we are very pleased to have Dié Wang from Brookhaven National Lab as our TEOS speaker today. Dié got her master's degree from the Nanjing Institute of Meteorology. Now it's called the Nanjing University of Information Science and Technology in China. Then she went to France to get her PhD in physics from Pierre and Marie Curie University. After that, she switched back to atmospheric science. She came to Brookhaven National Lab as a postdoc. And now she is an assistant scientist in the cloud process group. Dié was the recipient of the DOE Early Career Award. And that award is very competitive from my knowledge within the DOE enterprise. It's a competition across different labs and across disciplines, not just atmospheric science. So like DOE's climate program would be very pleased to have one of its investigators receiving this award. So it's not easy, and Dié is one of the recipients of this prestigious award. She is also the instrument mentor for rain gauges and distrometers for the DOE atmospheric radiation measurement facility. It is a national use facility for those of you who don't know. Today, her talk is going to be about updrafts and downdrafts in mesoscale convective systems. So, Dié, you can take over.
Yeah, thank you for the introduction, and thank you for having me here today. So today I'm going to talk about mesoscale convective systems, mainly about the updrafts and downdrafts associated with these systems. This work is in collaboration with Andres Pruin, Alexandra Ramos-Valley, and Mingge from NCAR. Also my colleague Scott Jangwande and Se Gupta from Brookhaven National Lab. So this is the outline of my talk. I will start with a brief introduction of mesoscale convective system and why they're important to weather and climate. And after that, I will be talking about unique observations that have been collected for study MCS updrafts and downdrafts. And finally, I will be focusing on the challenges that we're facing today in simulating MCSs, especially with kilometer scale models. So first, let me introduce MCS and their importance. For those of you who are not that familiar with MCS, you can think of them as individual cloud systems that aggregate, organize, developing into a single system. And they can produce precipitation covering a horizontal scale of hundreds of kilometers. As you can see from this animation here over the Michigan, you have a MCS initiated and propagated to the East Coast. You also have a lot of lightning flashes on top of it. So this is one of the typical MCS taps that we observed in the continental US. So why do we care about MCSs? One of the reasons is that the influence of these clouds extends far beyond the scale of an individual system. And they regulate the global energy cycle and drive large-scale atmospheric circulations. This plot on the right side shows you the number of MCSs occurred each year on a global scale. And you can see that in the tropical regions, we have a large number of MCSs detected each year. And there are a few MCS hotspots here in the tropical warm pool, and the other one in the Amazon basin. These Amazonia MCSs are, will be one of the targets of this talk. And these systems release a large amount of latent heat and power the rest of the globe. Secondly, MCSs play an important role in the Earth water cycle, producing a significant portion of the global precipitation. As you can see on the bottom panel, this shows you the precipitation fraction that comes from MCSs. And it's not surprising that over the tropical region, we have MCSs are a major contributor to the annual precipitation. Of course, there are strong seasonalities associated with the migration of the ITCZ of the region. But I want to draw your attention to the continental US. In the central region, you can see that the MCSs produce more than 50% of the annual precipitation there. And we are going to look into these MCSs in the following of the talk. Observations have shown that the climate extremes are worsening and the global warming scenario. And MCSs are part of that story. So previous studies have shown that MCSs are most likely being stronger and more frequent in the future climate over the US. For example, one study that led by Andres Pran in 2017, they did a ensemble of MCS simulations in the current and future climate conditions, and they found that the future MCSs tend to have a higher cloud top and a larger mass flux. And they also did a composite of surface precipitation properties for current MCSs on the left and future MCSs on the right. And the colors here represents the precipitation rate. And you can see that both the area and the intensity of the precipitation increase as we warm up the environment. According to their prediction, by the end of the 21st century, extreme MCSs may produce twice as much as precipitation compared to today. So it's concerning because you can imagine the flooding risk could be more severe than anticipated. Despite their importance in weather and climate, representing MCSs in these models are very challenging. One of the limitations with climate models is that they are unable to resolve convection at their natural spatial temporal resolutions. As you can see in this cartoon, oftentimes convection has to be parameterized in these models as individual convective towers. Getting these individual towers to be organized in these models is a very difficult task. However, recently, global and regional models have reached the convection-permitting scale with a grid spacing less than 5 kilometers. And this has significantly improved the representation of MCSs, especially their bulk properties, because we turn off the convection parameterization in these models. But large uncertainty persists in simulating those small-scale processes of MCSs, especially the updraft and downdraft properties. This has to do with the fact that the MCS processes are very complex. As you can see here in this cartoon on the right, there are lots of things going on in an MCS. For example, you have updrafts that transport moisture, momentum, and heat from near surface level to the upper troposphere. And you have phase transitions between different types of particles in the clouds. And these clouds also interact with the surrounding environment through entrainment and mixing processes. You also have aerosol convection interactions, precipitation, and cold pools. So it's a very complex system. And it's impossible for models to explicitly simulate all the aspects of an MCS. And in this talk, I'm not going to talk about everything, but I will highlight two major processes that regulate the life cycle of an MCS, which are updrafts and downdrafts. Another separate bottleneck is that we don't have a lot of great observations that can tell us more about MCS processes and also can be used to evaluate our model performance. We have satellite observations. These observations are great because that gives us a global view of MCS and their distributions. We can also analyze the variabilities of MCSs across different climate regions, but there's no vertical velocity observations from space yet. Although we have some future satellite missions such as INCUS and EarthCare, and they're targeting the estimations of updraft intensity. We also have aircraft measurements. These measurements are reliable and it's a direct measurement of vertical velocity, but these flights are very costly, and we don't usually fly through the very intense convective core because that is very dangerous. So because of that, we probably underestimate the updraft extremes in those convective cores. Then we have ground-based remote sensing techniques, and we can use those measurements to retrieve vertical velocity from ground level. And there are a couple of different ways of doing that. You can use multiple scanning radars or vertical pointing radars. Although there are limitations and uncertainties with these retrievals, but it remains the best option to study updrafts and downdrafts because we have long-term data records and in multiple locations. So in the next section, I will talk about one of the observations that we've collected and to study study the MCS updrafts and downdrafts. So most of the observational data sets that we'll be using in this study are from DOE Atmospheric Radiation Measurement, ARM user facility. So for those of you who are not that familiar with ARM, ARM is the largest and the most extensive climate research facility in the world. It provides comprehensive observations of clouds, precipitation, aerosols, and its surrounding environment. And not only we have such great data set and instrumentations, but we have those at a wide range of locations. So this map shows you all the places that ARM has been to in the past. And this map is a bit outdated. It was done in 2020, but and we have a few more today. But it shows you the idea of deploying those mobile facilities to different parts of the world to observe different types of clouds. Especially you have three fixed sites. One is in Oklahoma, the second one is in Azores, and also you have one in Alaska. So you have long-term measurements there in these two sites, but the rest of the dots show you those mobile facilities that were deployed to a location for a year or two. The most recent campaign that ARM conducted was the tracer field campaign in Houston, led by Mike Jensen at Brookhaven. And I know some of the Stony Brook folks were also involved in this campaign. For us, most of the observations we've been using are from two sites. One is in Oklahoma, US, and the other one is in the Amazon basin. So these two locations experience very frequent MCSs, as I've shown you in the introduction session. And we selected 20 MCSs from the Oklahoma site as mean latitude examples, and 60 MCSs from the Amazon site as tropical examples. So we did the selection based on scanning radar images as the one shown here. This is one of the Amazon cases. You have this very strong convective line with higher refractivities and also this broader stratform area behind that with lighter precipitation. So this is a typical feature that we're looking for on the satellite images. In this talk, I will only focus on the convective part of the storm where you have radar refractivity larger than 40 dBz. One of the key things that we're interested in is the vertical velocity. which is very important to MCS and is also something that is very hard to measure. The measurements that we've been using are from a special radar called radar beam profiler in ARM. Most of you may be familiar with the traditional radar beam profiler for retrieving horizontal winds, but ARM reconfigured these radar beam profiler to be vertically pointing, measuring the precipitation and clouds above. So what you get from the profiler is the radar refractivity and Doppler velocity. And we use those quantities to retrieve vertical air motion in clouds. And this plot shows you one of the Oklahoma cases. You have radar refractivity on the top panel as a function of time and height. And you have vertical velocity retrievals plotted on the bottom, also in the same time height space. The red colors here indicates updrafts and blues are downdrafts. So for this particular case, you have a very impressive anvil clouds at the leading edge of the convection, lasting for a couple hours. You also have a very strong convective core with a heavier precipitation at lower and middle levels. Then you have this broader trailing stratform area with bright band signature at melting level. So these are the typical gradients that, of an MCS. You may notice in the convective core, we have this wider updraft plumes that are mostly present in the middle and upper levels. We also have this precipitation-driven downdraft at the lower levels. So these are the updrafts and downdrafts that we will be focusing on in this talk. As I mentioned, we are interested in the mature stage of an MCS since it's the strongest phase. So we want to make sure that when the system passes over the arm site, it has a stronger cold pool and a larger rainfall rate at the surface. So we look at the surface measurement from ARM. One example shown here, you have a surface theta E as a function of time and surface rainfall rate as well. For this particular case at 15 UTC is the timing of the convective line passage, and you have a dramatic drop in surface theta E, which signifies a very strong cold pool. At the same time, the precipitation rate exceeds 80 millimeter per hour for this case. So we only look at these very strong cases in this study, and we did a composite based on the timing of the maximum rainfall rate for the selected cases. So here, what I'm showing is the composite of surface variables. You have theta E and relative humidity on the top panel, and rainfall rate and wind speed on the bottom panel. And Amazon cases are plotted in green, Oklahoma cases in yellow. The solid lines are mean values of this quantity, and shadings are standard deviation. You can see that these two locations show very similar cold pool strength and precipitation patterns. The drop in surface theta E is roughly 10 Kelvin, and the peak of rainfall rate exceeds 80 millimeter per hour. However, you do see some differences in terms of the relative humidity and wind speed. They both experience increase in relative humidity at the leading edge of the cold pool, but the Amazon cases are more saturated. However, the Oklahoma cases show a stronger gusty wind at the surface. We are also interested in the general structures of the MCS. So we also did a composite in a similar way as we did for the surface variables. And here on the top panel, you have radar refractivity, and on the bottom, you have 90 phase vertical percentile vertical velocity. Amazon cases on the left, Oklahoma cases on the right. And the time zero here indicates the timing of the maximum rainfall rate.
Maybe you can help to clarify why there is a wide band from 2.5 kilometer to 5 kilometer in the vertical velocity. It's masked.
Yeah, it's masked because this is the melting level. So the retrieval, so we have those melting particles, and you see we have strong radar refractive. Here you can see as well strong refractivity at the melting layers. So the retrieval of the vertical velocity isn't that accurate. So we mask that out in the melting layers. So we don't use those retrievals at these levels.
Okay.
So back to this plot, we see some similarities between these two systems. For example, we have this very consistent convective core right in the middle at both locations, and we have this trailing stratiform area with bright band signature at melting level. You have a little bit stronger stratiform precipitation in Oklahoma and a more consistent anvil clouds. In terms of the negative phase vertical velocity field, they both have very consistent updrafts in the middle and the upper levels around time zero. But in the Amazon, you have a little more consistent updrafts showing here compared to these noisy features in the Amazon in Oklahoma. Before digging too much into the quantitative comparison of the updrafts and downdrafts, we want to know the environment conditions that triggers these MCSs, and if they are similar or different between these two locations. So we did a composite of soundings that were launched within 6 hours prior to the MCS passages. We show the Amazon cases on the left, Oklahoma cases on the right. The green lines are dew point temperature profile, and red lines are temperature profile, and black lines are partial temperature profile. And the red shading indicates the cape, and blue shading is the scene. You can see they both have a lot of cape, especially in the middle and the lower levels. So that's a essential component to initiate those convective, those MCSs. But in Oklahoma, you do have a lot of scene at lower levels. So that means in order for those near surface level parcel to rise to the upper levels, they need to overcome a lot of negative energies. When the convection does fire, they tend to be stronger. And you may also notice this drier mid level in Oklahoma. So that could favor the evaporation during the precipitation processes, and then may lead to a stronger downdrafts. In contrast, Amazon condition is very moist throughout the entire troposphere, and you have a higher level of neutral buoyancy there, which suggests a higher cloud top. So then let's look at some statistics of vertical velocity profiles. Here, what I'm showing is the mean vertical velocity plotted as a function of cloud top height and height in y-axis. So Amazon cases on the left, Oklahoma cases on the right. So this is a more instructive way of showing the vertical velocity structures of different parts of the storm. For example, when you have a higher cloud top height, you are most likely in the deeper and center of the storm. So as expected, you may have a stronger vertical air motion here, as shown here, and it's much stronger for Oklahoma cases compared to the Amazon, because we have those a stronger background forcing, greater instability that is, as you saw in the previous slide. And the downdraft structures are also very different between these two locations. You see a deeper and stronger downdraft in Oklahoma compared to these shallower and weaker downdrafts in the Amazon. And one of the reasons could be the drier mid level in Oklahoma that favors the stronger evaporation that's stronger downdrafts. Another cool thing that we did with the high-resolution reducing profiler observations is to look at the updraft and detailed structures of updraft and downdraft cores. So here is an example of a updraft core that we identified for this particular case. And these cores are need to satisfy these thresholds that are listed here. And we did that for all the cases that we selected. But we also want to know the size of these cores. So because reducing profiler samples everything in time, so if we want to get a sense of how large these cores are, we need to multiply the time series by convection propagation speed. And this plot shows you how we estimate the propagation speed by looking at the convective echoes from each reader scan. And for detailed information about this method, you can check out Jaffon's 2018 paper. So now we have the size of each individual core. And I plotted a couple of different parameters as a function of the size of the core for updrafts. On the left, you have mean vertical velocity, and in the middle, you have mass flux. And on the right-hand side, you have a mean vertical velocity divided by maximum vertical velocity. So this mean to maximum vertical velocity ratio tells you something about the shape of the core or the variability inside the core. As you can see here, the updraft intensity and mass flux increase as a function of core size, which means that for those larger cores, they tend to be very intense. And this makes sense because those larger cores tend to be more likely to survive during the entrainment and mixing processes. It's surprising that we see a very similar trend in terms of the shape of the core. They are very similar in terms of the trend. So this suggests that for the cores that have the same size, their shape and their variability are not that different in these two particular locations. So what I've shown you previously are statistics and results from mature stage MCSs. But you may be curious how those updrafts and downdrafts would change as a function of their life cycle. So to explore that, we use a self-tracking algorithm called Toback to identify the cell initiation and follow the cell through their life cycle. And then we pick out those cells that are closer to the arm site, and we look at the vertical velocity profiles for these cores as a function of their life cycle. And we experiment these on isolated convective system first. That is the one you were seeing in the animation. So here on the right-hand side, what I'm plotting is the phase and negative phase percentile vertical velocity for different life cycle stages of those isolated convective cores. So you can see the red color represents developing stage, blues are mature stage, and yellows are dissipating stage. During the developing stage, you tend to have a stronger updrafts at lower and middle levels. These updrafts will accelerate the vertical extension of the core during this stage. And during the mature phase, you have a stronger updrafts and downdrafts at higher levels because this is the most this is the strongest phase. But during the decaying phase, everything gets weaker overall. So we demonstrated here that this method gives us a very detailed statistics of updrafts and downdrafts at the different stages of their life cycle. So we're going to perform a similar study, but for MCSs in the following work. So I've shown you all these cool results from the observational side. We want to know that whether these models can replicate these features and core size velocity relationships, especially those kilometer scale models. So why we are targeting kilometer scale modeling? As we know that the turbulent motion, as we go to higher resolution, we tend to better resolve the turbulent motion with the models. And this is very important to better simulate convective dynamics. But at the same time, you also increase the computational cost, especially when you get down to LES scale. And sometimes this can be very painful to handle. But from previous studies, we learned that those MCS bulk properties tend to converge at a resolution between 1 kilometer to 4 kilometer, and further refining the resolution to a higher, it doesn't add too much value to these properties. So we find a sweet spot here combining all these factors. In this model grid zone, we can get a reasonable representation of an MCS, especially their anvil size and precipitation extremes, also the propagation speed and directions, without spending too much computational hours. But within this model grid zone, we don't fully resolve the turbulent motion. So that will have an influence on the storm dynamics. So there is a question here, whether we get the right answers for the right reasons. In the following studies, I'm going to discuss the variabilities of updrafts and downdrafts within this model grid zone. So we collaborate with Andreas Prin at NCAR and his group. We did an ensemble of MCS simulations at different grid spacings. So here we started with this 12 kilometer runs with the convection parameterizations turned on. So you, as shown in this example, you have a something kind of like an MCS, but not quite yet. When going down to 4 kilometer scale, we see that we tend to get a multiple convective cores and also multiple overshooting tops. And these these individual cores these individual cores are organized, and you also see those newly initiated convective storms. With further refining the resolution to 1 kilometer, you really start to resolve the detailed structures of MCSs, and you get this very impressive cold pools. Also, those convections initiated along the cold pools. And going down to LES scale, 250 meter resolution, you get detailed structures of updrafts, also those nice anvil spreading and detailed structures at the cloud edges, and a more continuous cold pool here. So we do see some benefits of using a high resolution model. Let's summarize a little bit what we have here. So we did an ensemble of idealized MCSs with WRF at different model grid spacings from 12 kilometers to 250 meters. And the soundings to initialize these systems are closer to mid-latitude conditions. So we are going to compare these simulations with observations from the Oklahoma site. We are only looking at the mature stage of an MCS for now. And as you can see from this snapshot, at 12 kilometers, we have this giant updraft that dominates the convective area. We only have those shallow downdrafts at the cloud top. But when you get to the final resolutions, you start to resolve the narrower updrafts and downdrafts, and the fraction of the downdrafts increases in the high resolution models. And let's look at some quantitative comparison across different resolutions. You have cloud top temperature plotted on the top panel, and precipitation rate plotted on the bottom panel for model simulations at different resolutions. the most significant change that you are seeing here are from 12 kilometer to 4 kilometer. You see we get a larger anvil size and multiple overshooting cores, and also the precipitation pattern looks different. You have multiple precipitation cores, and also you see this newly initiated convective core. But within this kilometer scale range, the changes in terms of the cloud top structures are not that significant, and the precipitation patterns start to converge as well. Going down to 500 meters and 250 meters, you can see there are limited changes in terms of the anvil size and structures, and the precipitation patterns remain stable in these simulations. So it's fair to say that the MCS bulk properties tend to converge at a resolution closer to 1 kilometer. Is it the same thing for updrafts and downdrafts? So to answer that question, we plotted the maximum updrafts on the top panel and maximum downdrafts on the bottom panel as a function of cloud top height and height. So this is a similar plot as I've shown you earlier from the observations. And again, when you have a higher cloud top, you are most likely in the convective center or the deeper part of the storm. You tend to see a stronger updrafts and downdrafts overall. So it's consistent with observations, and we are happy there. But you may notice we have a stronger updrafts and stronger downdrafts when you get to higher resolution. This, especially for downdrafts, you start with this uniformly distributed, almost uniformly distributed downdraft features at 4 kilometer to this two-mode downdraft structures at 250 meter. You have the compensating downdrafts at the higher levels and precipitation-driven downdraft at the lower levels. If you were to compare with the observational data set, you can see that especially this high-resolution model, we overestimate the intensity of the updrafts. So this has been discussed in many previous studies already, and partially because we don't handle the entrainment very well in these models. And in terms of the downdraft, you do see an improvement, and we get closer to the observations. One of the reasons could be could related to the compensating effect from this overestimated updrafts. And you may notice we underestimate the downdrafts at the middle levels, and there could a couple of hypotheses to that. One of them could be we underestimate the grapple fractions. And also, this is sensitive to the macrophysical schemes that we used in the models. Another important aspect of the updraft and downdraft is how often do they occur in the convective core. So here to explore that, we plotted the updraft and downdraft probability as a function of height. And we only care about the very intense updraft and downdraft cores with a velocity larger than 5 meters per second. For updrafts, you can see that we have a peak in updraft likelihood in the middle levels between 5 kilometer to 7 kilometer, and it's consistent between observations and models. Different colors here indicates different resolution model results. And compared to this dotted line, which is the observations. But in all the models, you see we overestimate the probability of updrafts, which means we simulate too many updrafts in these models. But it's a different story for downdrafts here. We have we don't simulate enough downdrafts in these models, and especially at 4 kilometer, you see we barely see downdrafts at the middle levels. And with the higher resolution model, we get closer to the observations and we see improvements, but we're still far from the observations. And to further explore why we overestimate updraft intensity and probability, we look at those updraft and downdraft cores in a similar way as we did for observations. So we contour these updraft regions and we calculate the core intensity, mass flux, and the core size. And we compare those with the observational data set. So here, green is Amazon cases, yellow is Oklahoma cases, WRF simulations with 1 kilometer resolution in blue, and 250-meter runs in red. And this is a histogram of core size for updrafts. You can see we overestimate the population of those larger cores in these models. So remember, these larger cores tend to be very intense. So this is probably one of the reasons that we overestimate the updraft extremes with these models. And if we look at the problem in another way, it may not be that bad in these models. So here, what I'm showing is the mean vertical velocity for those cores as a function of their size. Here is for updrafts, and again, Oklahoma in yellow and model simulations in blue and red. You can see that for a core that cores that have the same size, we did a pretty good job of simulating their vertical velocity. In terms of the shape of the core, we do see improvements with a higher resolution model. For example, these 250-meter runs are very close to observations, but the 1 kilometer simulation is not quite there yet. Another thing that people won't always pay attention to is the downdraft core properties, and it's where we see most of the improvements. Here again, the higher resolution model are much better in terms of simulating the downdraft core vertical velocity, but we do see an underestimation of downdraft velocity for a specific core size. And in terms of the shape of the core, again, we see improvement with the high resolution models, but we still simulate two less variabilities inside the core. So with these results, we know that the 250-meter run, we may need a higher resolution model to better resolve those downdraft structures. So as you know, the model evaluation work is never easy and straightforward. It's the same thing here. So our readable profiler is a pencil point measurement in time and height. And the model simulations are oftentimes 3-dimensional snapshots. So even though we are very careful about the measurement uncertainties and the beam width and also the sampling biases in our analysis, but it's still not ideal. So we came up with this idea of putting a virtual readable profiler in the model domain to mimic what a real readable profiler would see as the storm passes over the site. And I show you an example of a model domain that we set up for Amazon cases. In the inner domain, we put 5 readable profilers next to each other and to sample different parts of the storm and also give us more statistical results. We did the simulation using a higher grid spacing of 125 meter because we want to further discover those downdraft properties. And we output those results at a very high temporal resolution of 5 seconds. This is comparable to what a readable profiler measurement would give us. So let me show you some preliminary results here. On the left-hand side, you have a typical cross-section of an MCS in the Amazon, simulated at a 125-meter resolution. The axis is the longitude, and y-axis is the height. On the right, you have a virtual readable profiler simulations for the same event. but the x-axis is the time, and the y-axis is again is the height. So instead of getting these individual updraft and downdraft cores in a specific time step, we captured the evolution of an updraft with the virtual profiler. You can see you have this updraft initiates near surface, and as they rise and expand to the upper levels, we do capture the evolution. It's more clearly from this theta E field. You see you transport the higher theta E air with the updrafts and all the way to the upper troposphere. So we are very excited about these results. We are still simulating some of the SGP cases. In the following studies, we are going to compare these simulations with the radar wind profile observations and with the focus on downdraft properties. So this is all I have for today, and I'd like to summarize a little bit all the things we have here. We have a great observational data set from ARM that we can use to study MCS properties, especially their updrafts and downdraft structures. And also we came up with some interesting matrices to evaluate the model performance. We also compared the MCSs initiated in Oklahoma in two different climate conditions, in Oklahoma and Amazon, and we found that the Oklahoma cases have a stronger updrafts and downdrafts compared to the Amazon because of their stronger background forcing and greater instability in that condition. We also explore those model simulations, especially with the kilometer scale model, and to see whether they can get a reasonable representation of MCSs and also their updrafts and downdraft properties. We found that the high resolution model might best match with observations in terms of the draft core size velocity relationship, but a higher resolution model may be needed to better resolve the downdraft velocity and probability. Of course, there are a lot of things left, and we want to focus on in the future work. We want to continue this life cycle study for MCS convective updrafts and downdrafts, and this is going to be a very important data set to evaluate our models. We are also curious to know whether the model macrophysical schemes and boundary layer schemes could have an impact on MCS dynamics. So we're going to do some sensitivity tests on that. Another thing that is also a major focus of my early career project is the aerosol impacts on convective clouds. And we started with the isolated convective system, but eventually we are also interested in looking at those impacts on MCS life cycles. So that's all I have for today, and I'm happy to take any questions that you may have.
Thank you, Dié, for this very interesting talk. Now let's take questions from the audience. Kamazima, you are muted.
Yes, sorry. Thank you, Dié, for a great talk. There are some things I missed because I'm an oceanographer, but I was in your conclusions and the future work you're planning, you didn't quite mention the structure uncertainty, and it looks to me that maybe the uncertainty in the structure is still there. And the reason I say that is based on your slide 18, the right-hand panel where you are looking at the structure. Yeah, that one. So when you look at that, you have an R of 0.3, and I'm wondering how significant is that to really get a conclusion on what the structure is like. And my second question, not related to this, was this slide number 8. You don't need to go to that one. What I noticed was in South America, there was less rain, less precipitation associated with the MCS relative to the Congo area and the Asian area. And I wondered whether you could go back and touch on that. Maybe it might also have implications on what you showed. Thank you.
Yeah, so to answer your first question here, the uncertainty here, yes. So this is not a significant, not a very significant coefficient, but it shows you the trend in the of the vertical velocity versus core size, and yes, there are uncertainties related to these reductant profiler measurements. And of course, the large arrow bar here you are seeing is because we bin all these cases, into 1 kilometer size bins. But I think this relationship makes sense. We also see a similar thing in the models. But of course, this needs to be further evaluated using more cases and cases at more locations. I hope that we can have more vertical velocity data to better understand these relationships. Maybe the future satellite mission would help us in that way. In terms of your second question, I forgot the plots that you were talking about.
Slide 8, I believe.
Slide 5. It was 5.
5. Okay.
I'm sorry. Yeah. What was the question again?
So in there, what you notice, you see the area around South America, the MCS. I was looking at the MCS hotspot. Is very strong in the upper panel, but in the lower panel, the precipitation that goes with that is reduced when you compare it to the area, say, around Congo, and also the area in the Asian region.
Yeah, so this is the number of MCSs detected, right? But this is the fraction of precipitation from that MCS. But in the Amazon, we also have lots of other types of convections. For example, those isolated convections that are not in this plot. So MCS only account for 50% of the precipitation there, but the other 50 may be related to isolated and other types of storm. But in other regions, for example, here, when you get a storm, maybe they are just MCSs.
Okay.
But I didn't do a study on that, so that would be my guess.
Thank you.
Okay, Michael.
Yeah, this is really great work. It's been a while since I read Scott's papers. Do you run into any issues with attenuation, or is it just that the frequency is so low that it's not really an issue?
That would be a question for Scott, but
I mean, it doesn't. Looking at those data, it doesn't look like it. So maybe not. I guess my other question was, I know the beam width is pretty large, if I recall correctly. Do you have any concern that, especially at upper parts of the storm, that you're not really getting a good indication of peak vertical velocities because of that?
Yeah, definitely. We get a larger beam width at the higher levels and a smaller, a narrower beam width at the lower levels. Exactly. I think if we do an estimation on the relative resolution of that, is equivalent to 1 kilometer or less in the middle and the lower part. So it's a very high resolution observations, but the higher levels, of course, it smears out a little bit because of the beam width, and we do have a larger uncertainty there. Yeah.
Just one more question. When you're estimating the basically the sizes of the updrafts. Do you have to assume that the MCS is moving perpendicular to the radar? Because I'm imagining something that was moving like from south-southwest to north-northeast and was kind of training over the radar. You would get an idea that the updraft core was larger than it actually is. So do you have to make some sort of adjustment for the angle of how the MCS is moving relative to the radar?
That's a very good point. We didn't.
I mean, I'm guessing in most cases, you know, it's probably not a huge deal. I was just curious, you know, if that's something that you ran into. I'm guessing in most cases it's mostly, you know, moving west to east, right past the radar system. But yeah, I guess that's just something to consider. Thanks. This was really great work.
Yeah, this is definitely something we can check with the observations and also with the simulations.
Okay, so I have a question, simple question. In the simulations for the resolution sensitivities, it looks like you simulated the real cases. So is the model initialized based on real conditions, or it's idealized initialization?
So in the first part, the results that I showed with the comparison between observations and simulations, those are for idealized simulations. So we initiate those MCSs using soundings and co-pools. But in the following study, using the virtual radar wind profiler, that simulation we initiated using a real case setup, forcing data.
So the simulation model is the WRF or the CM?
Yeah, it's the WRF.
Okay. So it has the capability to do real condition initialization.
Yes.
Okay. Mm-hmm.
The capability there.
Yeah. Are there any other questions? If not, then let's thank Dié again for this wonderful talk.
Yeah, thank you all. And thank you for the invitation.
Yeah, so we will not be able to arrange the group meeting we usually do for in-person seminar. If you need to speak to Dié, you can either email me or contact Dié directly. With this, then thank you for your participation. Thank you, Dié. Bye-bye.
Yeah, thank you, Minhua.